What if I told you that right now, at this very moment, the oldest light in the universe is passing through your body? An echo from the beginning of everything, traveling for nearly 14 billion years to reach you. Can you imagine what secrets it carries? What stories does it tell about the first moments of creation? Together, we are about to embark on a journey unlike any other. We will travel back to the edge of time itself to witness the birth of light and discover how the faintest whisper from the cosmos reveals the deepest truths about existence. We live our lives immersed in an invisible ocean. All around us, passing through walls and flesh and bone, waves of ancient radiation flow endlessly. You cannot see them with your eyes or feel them with your skin, yet they are as real as the ground beneath your feet. This is the cosmic microwave background, the CMB, and it is quite literally everywhere. In every cubic centimeter of space, in the room where you sit right now, thousands of these photons are streaming past you every second. They have been traveling since before the Earth existed, before our sun ignited, before our galaxy took its spiral shape. But what exactly are these mysterious waves? To understand them, we must first understand what they once were. The photons that make up the cosmic microwave background were not always so cold and dim. 13.8 billion years ago, they were born in a furnace of unimaginable heat and density. They were the light of creation itself, blazing with the energy of the newborn universe. Today, they have cooled to just above absolute zero, stretched and reddened by the expansion of space itself. What was once a blinding inferno is now a gentle whisper, barely warmer than the void. Can you grasp the scale of what this means? Every direction you look, in every corner of the observable universe, this radiation fills space uniformly. It is the closest thing we have to a universal constant, a cosmic background against which everything else exists. When astronomers first detected it, they did not immediately understand what they had found. Could they? They had stumbled upon proof of something almost incomprehensible, evidence that the universe itself had a beginning, that there was a moment before which nothing we know existed. The CMB is the fossil record of that moment, preserved in light. Think about this for a moment. When you watch television static on an old analog screen, about 1% of that visual noise is caused by the cosmic microwave background. Photons from the birth of the universe are literally creating tiny flickers on your television. Is that not extraordinary? The echo of creation manifesting as snow on a screen. We are so deeply embedded in this ancient light that it becomes part of our everyday technology, part of the background hum of existence. We swim in the afterglow of the Big Bang without even realizing it. To truly appreciate what we are about to explore, we must shift our perspective. We must learn to see with different eyes, to perceive wavelengths of light invisible to our biology. The cosmic microwave background does not live in the visible spectrum. It exists in the microwave range with wavelengths measured in millimeters. This is why we cannot simply look up and see it painting the night sky. We need special instruments, radio telescopes that can detect these faint whispers and translate them into images we can comprehend. But make no mistake, just because we cannot see it does not mean it is not there. Let us imagine together what it would be like if we could see microwaves with our naked eyes. Picture yourself standing outside on a clear night. Instead of the familiar darkness punctuated by stars, the entire sky would glow with a uniform, gentle warmth. Not bright, but present. A soft amber radiance surrounding you in every direction, unbroken by clouds or horizons. Within that glow, you might notice something extraordinary. Tiny variations in brightness, patches just slightly warmer or cooler than their neighbors. But these are not random. They are the fingerprints of creation, the seeds from which all structure in the universe would eventually grow. As we prepare to journey deeper into this mystery, I want you to hold one thought in your mind. The light we are about to study left its source when the universe was just 380,000 years old. In cosmic terms, that is infancy. The universe is nearly 14 billion years old now, which means this light has been traveling for almost the entire history of existence. It has crossed distances so vast that the space itself expanded while it traveled, carrying it further than any object could move through space alone. What does it feel like to contemplate such a journey? This is where our journey truly begins. Together, we will trace these ancient photons back to their origins. We will witness the moment they broke free from the primordial plasma and began their eternal voyage. We will see how tiny imperfections in their distribution would eventually sculpt galaxies and stars and planets. We will stand at the edge of the knowable universe and gaze into the face of creation itself. And perhaps, in doing so, we will find a sense of peace in knowing that we are connected to something far greater and older than ourselves. Are you ready? Then let us begin our descent into deep time. Our story of discovery begins not with visionary cosmologists or theoretical physicists, but with two radio astronomers trying to solve an engineering problem. The year was 1964, and at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson were working with a large horn antenna originally designed for satellite communications. They were meticulous scientists, determined to eliminate every source of interference and noise from their instrument. What they did not know was that they were about to stumble upon one of the most important discoveries in the history of science. Sometimes, the universe reveals its secrets not to those who seek them, but to those who are patient enough to listen. Penzias and Wilson were puzzled. No matter what they did, no matter how they oriented their antenna or when they made their observations, they detected a persistent hiss of radio noise. It was uniform, unchanging, and utterly mysterious. At first, they suspected everything. Equipment malfunction, interference from nearby New York City, radio signals from the ground. They even considered that pigeons nesting inside the antenna might be the culprit. Yes, you heard that correctly. These brilliant scientists thoroughly cleaned out pigeon droppings, what they diplomatically called a white dielectric material, convinced that this might be the source of their mysterious signal. But even after the pigeons were relocated and the antenna was scrubbed clean, the hiss remained. The signal was the same everywhere they pointed, day and night, summer and winter, north, south, east, west. It was as if the entire sky was generating this faint radio whisper. The temperature of the signal was cold, just a few degrees above absolute zero, about 3 degrees Kelvin to be precise. They measured and remeasured, checked and rechecked their calibrations. Every test confirmed the same result. This was real. But what could possibly cause a uniform radio signal coming from all directions? Penzias and Wilson were observational scientists, brilliant at operating equipment and gathering data, but they did not yet understand what they had discovered. For that, they would need theoretical physicists to connect the dots. Meanwhile, just a few miles away at Princeton University, a team led by physicist Robert Dicke was building their own antenna with a very specific goal. They were searching for exactly what Penzias and Wilson had already found: the relic radiation from the Big Bang. Decades earlier, in the 1948, physicists George Gamow, Ralph Alpha, and Robert Herman had predicted that if the universe began in a hot, dense state, there should be leftover radiation from that primordial fireball, cooled by billions of years of cosmic expansion. They had even calculated its temperature. It should be just a few degrees above absolute zero. The prediction had been largely forgotten by the scientific community, but Dick and his team remembered. When Penzias and Wilson heard about the Princeton team's work, the pieces fell into place. The phone call was made. Conversations were had. papers were written. In May of 1965, 2 publications appeared side by side in the Astrophysical Journal. Penzias and Wilson described their observations of the unexplained excess antenna temperature. Dick and his colleagues explained what it meant. The hiss was not noise at all. It was signal. It was the echo of the Big Bang, stretched and cooled but still reverberating through the cosmos. The 2 radio astronomers had detected the oldest light in the universe by accident, and in doing so, they had provided the strongest evidence yet that the universe had a definite beginning. Imagine being in their position for a moment. You are trying to eliminate an annoying source of interference, and instead you discover proof that the entire universe exploded into existence 13 billion years ago. How would that feel? The profound found in the mundane, the cosmic hidden in the technical. This is the beauty of science. The universe does not care about our expectations or our assumptions. It simply is, and it rewards those who are careful and persistent with glimpses of truth. Penzias and Wilson would eventually receive the Nobel Prize in Physics in 1978 for their discovery. They had given humanity a gift beyond measure, a way to see the universe as it was in its infancy. The discovery of the cosmic microwave background was more than just a scientific achievement. It was a philosophical revelation. For thousands of years, humans had wondered about origins. Wait, how did everything begin? Was there always something, or was there a moment of creation? Different cultures and religions had offered their answers, but now science could contribute its own evidence. The universe, it seemed, was not eternal and unchanging. It had a birthday, and we could detect the light from that birthday still shining all around us. In that moment, cosmology transformed from speculation into an observational science. We could now study creation itself. Before we travel back to the moment when the cosmic microwave background was created, we must first understand what light truly is. We experience it every day as the brightness that allows us to see, but light is far more than simple illumination. Light is electromagnetic radiation, a traveling wave of electric and magnetic fields that propagates through space at the fastest speed possible in our universe. Nothing can travel faster than light. Not matter, not energy, not information. The speed of light is woven into the very fabric of space-time itself, a universal speed limit that shapes the nature of causality and existence. Every photon, every quantum of light travels at this cosmic speed limit. But here is something remarkable. Light comes in many forms, differing only in the length of their waves. The visible light that your eyes can detect is just a tiny sliver of a much broader electromagnetic spectrum. On one end, you have radio waves with wavelengths measured in meters or even kilometers. Then come microwaves measured in centimeters and millimeters. This is where the cosmic microwave background lives. Moving up in energy, you encounter infrared, the warmth you feel from the sun on your skin. Then visible light itself, the rainbow of colors your eyes perceive. Beyond that, ultraviolet light, X-rays, and finally gamma rays, the most energetic light in the universe. All of these are the same phenomenon, just with different wavelengths. Think about what this means. The radio signals carrying music to your car, the microwaves heating your food, the sunlight growing plants, the X-rays revealing your bones. These are all fundamentally the same thing. They are all light, all electromagnetic radiation, differing only in their energy and wavelength. Your eyes evolved to see only a narrow band because that is where our sun emits most of its energy. But if you had different eyes sensitive to other wavelengths, you would perceive an entirely different universe. You might see the heat radiating from living things in infrared, or the high-energy processes in distant galaxies emitting X-rays. The universe is alive with light we cannot see. Now, here is where our journey to understand the cosmic microwave background takes a crucial turn. Light does not just travel through space, it also travels through time. Because light has a finite speed, when you look at anything, you are seeing it as it was in the past. When you look at your hand, you see it as it was a few nanoseconds ago, the time it took for light to travel from your hand to your eyes. When you see the moon, you see it as it was 1.3 seconds in the past. The sun appears as it was 8 minutes ago. The nearest star system, Alpha Centauri, shows itself as it was 4.3 years ago, and distant galaxies reveal their ancient light from billions of years in the past. This is one of the most profound insights in all of astronomy. Telescopes are not just magnifying glasses, they are time machines. The further out we look, the further back in time we see. And the cosmic microwave background is the ultimate expression of this principle. It shows us the universe not as it is today, but as it was 13.8 billion years ago, just 380,000 years after the Big Bang. When those photons began their journey, there were no stars, no galaxies, no planets, no life. Just a nearly uniform sea of hot gas beginning to cool in the expanding cosmos. Those photons have been traveling ever since, and we are here to catch them after their impossibly long journey. But there is something else we must understand about light before we continue. Light can be redshifted. This is a consequence of the expansion of the universe itself. When space expands, it stretches the wavelengths of light traveling through it. A photon that started its journey as high-energy visible light might arrive as low-energy infrared or microwave radiation. This is not because the photon lost energy to some friction or collision. It is because the very fabric of space through which it traveled expanded, stretching the wave along with it. This is why the cosmic microwave background, which started as visible and even ultraviolet light in the hot early universe, arrives today as microwave radiation. Space itself has stretched it during its journey. Imagine you are a photon, born in the intense heat of the early universe. Your wavelength at birth is that of visible light, perhaps even the blue end of the spectrum, energetic and short. You begin your journey through space, but space itself is expanding. With every passing million years, the distance between galaxies grows, and so does your wavelength. You shift from blue to red to infrared to microwave. By the time you reach Earth 13 billion years later, you have been stretched into a long, lazy wave a few millimeters in length. You have cooled from thousands of degrees to just 3 degrees above absolute zero. But you have survived. You carry within you information about the universe's infancy, and you are about to deliver that message to curious creatures on a small blue planet. This understanding of light and its journey prepares us for what comes next. We are about to witness the moment when the cosmic microwave background was born. The moment when the universe transformed from opaque to transparent. The moment when light broke free from matter and began its eternal voyage. We will travel back to an era so early that the universe was a very different place, so hot and dense that the physics governing reality were almost unrecognizable. Are you ready to see the universe in its infancy? Then close your eyes for just a moment, take a deep breath, and prepare to journey back through 13.8 billion years of cosmic history. Let us witness creation. In the beginning, there was no space as we understand it. No matter, no energy. And then, from a singularity of infinite density and temperature, the universe exploded into existence. We call this moment the Big Bang, though it was not an explosion in space, but rather an explosion of space itself. In the first fraction of a second, everything that would ever exist was compressed into a volume smaller than an atom. The temperature was unimaginably high, trillions upon trillions of degrees. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were unified into a single force. This was the Planck epoch, and the laws of physics as we know them did not yet apply. Within the first trillionth of a second, the universe underwent a period of exponential expansion called inflation. Space itself expanded faster than the speed of light, growing from subatomic size to perhaps the size of a grapefruit in an incomprehensibly brief instant. This might sound like it violates what I just told you about light speed being the universal limit, but there is no contradiction. Nothing moved through space faster than light. Space itself expanded, carrying matter and energy along with it. During inflation, the universe cooled rapidly, and the fundamental forces began to separate from one another. First, gravity split off, then the strong nuclear force. The universe was taking its first steps toward the reality we inhabit today. After inflation ended, the universe continued to expand, but at a more sedate pace. It was still extraordinarily hot and dense, filled with a roiling soup of fundamental particles. Quarks, electrons, photons, neutrinos, all jostling in a state of thermal equilibrium. The temperature was so high that atomic nuclei could not form. Any protons and neutrons that came together would be immediately blasted apart by the intense radiation. The universe at this moment was a plasma, a state of matter where electrons are separated from atomic nuclei. It was completely opaque, like being inside a glowing fog so thick that light could only travel a tiny fraction of a distance before colliding with another particle and scattering in a new direction. But the universe kept expanding, and as it expanded, it cooled. About 1 second after the Big Bang, the temperature had dropped enough for quarks to bind together into protons and neutrons. About 3 minutes in, conditions were right for nuclear fusion to occur, creating the first atomic nuclei. Hydrogen nuclei, just single protons, and helium nuclei, made of 2 protons and 2 neutrons, formed in vast quantities. A tiny amount of lithium was also created. This is called Big Bang nucleosynthesis, and it is why even today the universe is roughly 75% hydrogen and 25% helium by mass. Every atom of helium in your body, in the sun, in every star you see, was forged in those first 3 minutes after creation. Yet even though atomic nuclei now existed, the universe remained opaque. The temperature was still too high for electrons to bind to those nuclei and form complete atoms. Free electrons roamed the cosmos, and photons could not travel far before scattering off one of these electrons. If you could somehow have existed in this era and opened your eyes, you would see nothing. Not darkness, but an all-encompassing glare. Light everywhere, but no images, no shapes, no shadows. Just pure, undifferentiated radiance. The universe was like the inside of a star, filled with light but impossible to see through. This state would persist for hundreds of thousands of years as the cosmos continued its relentless expansion and cooling. For 380,000 years after the Big Bang, the universe expanded and cooled. From billions of degrees to millions, from millions to thousands. The density of matter decreased as space stretched. And finally, the universe reached a critical threshold. the temperature fell below about 3,000 degrees. Kelvin, cool enough for electrons to bind to atomic nuclei and form the first neutral atoms. This moment is called recombination, though that name is slightly misleading because the electrons and nuclei had never been combined before. Nevertheless, the name stuck, and it marks one of the most important transitions in cosmic history. Matter as we know it began to exist, and then something extraordinary happened. With electrons now bound into atoms, there were far fewer free charges available to scatter photons. Light, which had been trapped in an endless dance of scattering for 380,000 years, suddenly found itself free to travel. In an instant, cosmically speaking, the universe transformed from opaque to transparent. For the first time since the Big Bang, photons could stream across space unimpeded. This moment is called the surface of last scattering because it is the last time these photons scattered off matter before beginning their long journey to us. Every photon in the cosmic microwave background last interacted with matter at this moment, and they have been traveling freely ever since. Try to imagine what this moment was like. For nearly 400,000 years, the universe had been a glowing fog. And then, suddenly, it became transparent. If you could have watched from some impossible vantage point, you would have seen the fog lift, revealing a universe filled with neutral gas, glowing at about 3,000 degrees, roughly the temperature of the surface of a cool star. This is the light we detect today as the cosmic microwave background. It has been traveling across the expanding universe ever since, cooling and redshifting with every passing eon. When it was released, it was visible light, perhaps orange or red. By the time it reaches us, it has cooled to microwave radiation just 3 degrees above absolute zero. But it is the same light, bearing the same information, waiting to tell us its story. Let us return now to the present day. We have traveled back to witness the birth of the cosmic microwave background, and now we must understand how we observe it and what it tells us. When astronomers point their radio telescopes at the sky and tune them to microwave frequencies, what do they see? At first glance, the CMB appears remarkably uniform. In every direction, the temperature is almost exactly the same, about 2.725 degrees Kelvin. This extraordinary uniformity was one of the first things that puzzled scientists. How could regions of space that have never been in contact with each other all have exactly the same temperature? This is called the horizon problem, and it was one of the mysteries that led to the theory of cosmic inflation. Look closer. If you could measure the temperature with exquisite precision, you would begin to see something extraordinary. The uniformity is not quite perfect. There are tiny variations, patches of sky that are slightly warmer or slightly cooler than average. These fluctuations are incredibly small, just a few millionths of a degree. If the average temperature is 2.725 Kelvin, the hottest spots might be 2.72503 Kelvin, and the coldest spots might be 2.72497 Kelvin. These are deviations of about 1 part in 100,000. To put that in perspective, if you were looking at a perfectly smooth wall, these variations would be like bumps and dips, only 1/10 of a millimeter high on a wall, 10 meters tall. These tiny fluctuations are the most important features of the cosmic microwave background. They are not random noise. They are real variations in the density and temperature of the early universe, imprinted on the CMB at the moment of last scattering. Think about what this means. We are seeing the lumpy distribution of matter when the universe was only 380,000 years old. These small overdensities, regions where there was slightly more matter than average, are the seeds from which all cosmic structure would eventually grow. The galaxies, the clusters of galaxies, the vast cosmic web that spans the universe today, all of it grew from these tiny ripples in the primordial plasma. But where did these fluctuations come from? Why was the early universe slightly denser in some places and slightly less dense in others? The answer takes us back to the very first moments, to the era of inflation. During that period of exponential expansion, quantum fluctuations, tiny random variations at the subatomic level, were stretched to cosmic size. These microscopic quantum uncertainties became the macroscopic density variations we see in the CMB. The universe, it seems, was born with a pattern already written into it, a pattern that would determine where galaxies would form billions of years later. From the quantum to the cosmic, from the smallest scales to the largest, this connection is one of the most beautiful insights in all of cosmology. The pattern of fluctuations in the CMB is not completely random. It has a characteristic scale and structure. The hot and cold spots are not evenly distributed in size. There is a preferred angular scale, about 1 degree on the sky, where the fluctuations are strongest. Plant. This is no accident. This scale corresponds to the distance that sound waves could have traveled through the primordial plasma before recombination froze the pattern in place. Yes, you heard correctly. Sound waves. In the hot, dense plasma of the early universe, pressure waves, essentially sound, rippled through the matter and radiation. These acoustic oscillations created peaks and troughs in density, and when the universe became transparent, those peaks and troughs were imprinted on the CMB as the hot and cold spots we observe today. These acoustic peaks in the CMB power spectrum, as scientists call them, tell us an incredible amount about the universe. By measuring the precise locations and heights of these peaks, cosmologists can determine fundamental parameters of reality. The geometry of space, the total amount of matter and energy, the rate of cosmic expansion, the proportion of ordinary matter versus dark energy. All of this information is encoded in the pattern of hot and cold spots in the CMB. It is as if the universe left us a message in the oldest light, a cosmic Rosetta Stone that allows us to decode the fundamental nature of existence. And we have learned to read that message. Imagine if you could somehow see the CMB with your own eyes, rendered as visible light instead of microwaves. You would see a sky painted with the gentlest imaginable variations of color. Not the dramatic reds and blues of false color images, but subtle shifts from one hue to an almost identical neighboring hue. It would be like looking at a sky made of soft watercolor, where the artist's brush had created clouds of barely perceptible warmth and coolness. You would be seeing the universe's baby picture, a snapshot of reality when everything was nearly uniform, but not quite. And in that not quite, in those tiny departures from perfection, lay the seeds of everything that would come after. Including you. We have seen the temperature map of the cosmic microwave background, those tiny fluctuations frozen into the light from the early universe. Now we must understand what happened next. How did these small ripples in density, these barely perceptible variations, grow into the magnificent cosmic structures we see today? The story is one of gravity, time, and the inexorable amplification of small differences. After recombination, when the CMB photons began their free journey across space, the universe was still mostly uniform gas. Hydrogen and helium spread nearly evenly throughout expanding space. Quite evenly. In some places, there was a little more matter than average. In others, a little less. And gravity began its patient work. Gravity is an attractive force. Where there is more mass, gravity is stronger. The regions of space that were slightly denser than average had slightly stronger gravitational fields. This caused matter from the surrounding, less dense regions to fall inward. As matter accumulated, these over-dense regions became even denser, and their gravity grew stronger still. This is a runaway process, a positive feedback loop. The rich get richer, gravitationally speaking. Over millions and tens of millions of years, small density contrasts of 1 part in 100,000 grew into density contrasts of 2 to 1, then 10 to 1, then 1,000 to 1. Matter began to collapse into concentrated clumps, while the spaces between them grew emptier. The pattern of collapse was not random. Remember those acoustic oscillations we discussed? The sound waves in the primordial plasma? They left their mark. The preferred scale of those oscillations meant that matter began to collapse on certain characteristic sizes. Smaller structures formed first. These were the seeds of the first dark matter halos, invisible clumps of dark matter that would later attract normal matter. Dark matter, which does not interact with light or normal matter except through gravity, could collapse more easily than ordinary matter. It acted as the gravitational scaffolding upon which visible structures would eventually assemble. The universe was preparing to light up, but it needed dark matter to set the stage. About 100 million years after the Big Bang, something remarkable happened. In the densest regions where matter had collapsed most efficiently, the gas became so concentrated that the temperature and pressure at the centers rose dramatically. Eventually, conditions became extreme enough to ignite nuclear fusion. Hydrogen atoms began to fuse into helium, releasing enormous amounts of energy. The first stars ignited. This era is called cosmic dawn, and it marked the end of the so-called dark ages of the universe. For the first time since recombination, the universe was illuminated by something other than the fading glow of the Big Bang. New light, generated by fusion, pierced the darkness. The cosmic story was entering a new chapter. These first stars were different from the stars we see today. They formed from primordial gas that contained only hydrogen and helium with no heavier elements. This meant they could grow to enormous sizes, perhaps 100 or even several hundred times the mass of our Sun. They burned hot and fast, with surface temperatures reaching tens of thousands of degrees, giving them an intense blue-white color. And they lived brief, violent lives. Within just a few million years, the most massive of these first stars would exhaust their nuclear fuel and explode as supernovae, forging heavy elements for the first time and seeding the cosmos with carbon, oxygen, nitrogen, iron, and all the other elements that make life possible. They were the cosmic alchemists, transforming primordial simplicity into chemical complexity. As more and more stars formed, they began to organize themselves into larger structures. Gravity pulled them into groups, into clusters, and eventually into the first small galaxies. These early galaxies were tiny compared to modern giants like the Milky Way, perhaps just a few % of the mass. But they were the building blocks. Over time, galaxies merged with one another, growing larger through cosmic collisions and acquisitions. The hierarchical assembly of structure continued, with small objects merging to form larger ones, and larger ones merging to form larger still. The universe was constructing itself from the bottom up, following the blueprint written in those tiny fluctuations in the cosmic microwave background. By about 1 billion years after the Big Bang, the universe was a vastly different place than it had been at recombination. Countless galaxies now dotted space, each containing millions or billions of stars. These galaxies were not randomly scattered but organized into a cosmic web, a vast network of filaments and walls surrounding enormous voids. This structure, the largest pattern in nature, had grown directly from those tiny density fluctuations in the CMB. If you could map the locations of galaxies today and compare it to the CMB temperature map, you would see the correlation. Hotspots in the CMB predicted regions where galaxies would form. The universe had followed the recipe written in its infancy, and so we arrive at the present day. The universe has been evolving for 13.8 billion years since the Big Bang. The tiny fluctuations we see in the CMB, variations of just 1 part in 100,000, have been amplified by gravity into the spectacular structures we observe. Galaxies, stars, planets, and yes, even you. Every atom in your body except for hydrogen was created in the interior of a star or in a supernova explosion. That star formed in a galaxy that grew from a dark matter halo that collapsed in a region where the CMB was slightly warmer than average. You are not just in the universe. You are of the universe. You are a pattern that emerged from those primordial ripples, a way for the cosmos to know itself. The accidental discovery by Penzias and Wilson in 1964 was just the beginning. Once scientists understood what the cosmic microwave background was, they realized its immense value as a tool for understanding the universe. But those early observations were crude. They could measure the average temperature of the CMB, confirming its uniform nature, but they could not detect the tiny fluctuations. The variations were simply too small, hidden in the noise of the instruments. For decades, cosmologists predicted that these fluctuations must exist. The seeds of cosmic structure had to be there, but proving it required technology that did not yet exist. The quest to map the CMB with precision became one of the great scientific endeavors of the late 20th century. The breakthrough came from space. In 1989, NASA launched the Cosmic Background Explorer satellite, known as COBE. For the first time, humanity placed an instrument above the obscuring effects of Earth's atmosphere, dedicated solely to measuring the CMB with unprecedented accuracy. COBE had two main goals. First, to measure the spectrum of the CMB with extreme precision, verifying that it truly was black-body radiation from the Big Bang. Second, to search for those elusive temperature fluctuations. The wait for results was agonizing as the satellite meticulously scanned the sky over several years. And then, in 1992, the COBE team made an announcement that would change cosmology forever. They had found the fluctuations. The first all-sky map of CMB temperature fluctuations was a revelation. It was crude by modern standards, with resolution measured in degrees rather than arc minutes, but it was definitive. The map showed exactly what theory predicted. Tiny variations in temperature arranged in a complex, cloud-like pattern across the sky. Some regions slightly warmer than average, glowing with a hint of excess energy from the early universe. Other regions slightly cooler, darker, representing subtle deficits in density. The lead scientist, George Smoot, described it poetically. "If you are religious," he said, "it is like looking at the face of God." The universe had revealed its blueprint, and it was beautiful. COB provided the big picture, but cosmologists wanted more. They needed higher resolution maps to study the fluctuations in detail and extract precise cosmological parameters. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP. This satellite was a significant technological leap beyond COB, with improved sensitivity and resolution. WMAP would observe the CMB for 9 years, producing maps of stunning clarity. For the first time, scientists could clearly see the characteristic angular scale of the fluctuations. They could measure the acoustic peaks in the power spectrum with precision. And from these measurements, they determined fundamental properties of our universe to within a few % accuracy. WMAP transformed cosmology from a field of rough estimates into a precision science. The WMAP data produced a map that became iconic in the scientific community. It showed the CMB fluctuations with about 30 times better resolution than COBE. The cloud-like patterns were now crisp and detailed. You could see structures on multiple scales, from large patches spanning tens of degrees to smaller features just a degree or two across. The map confirmed what the best theories predicted. The universe is flat, meaning its geometry is Euclidean on the largest scales. It is composed of about 5% ordinary matter, about 27% dark matter, and about 68% dark energy. It is 13.7 billion years old. These conclusions, drawn from the patterns in the CMB, were revolutionary in their precision and confidence, but the quest for even greater understanding continued. In 2009, the European Space Agency launched Planck, the most sophisticated CMB observatory ever built. Planck observed at multiple frequencies with even better angular resolution than WMAP, allowing it to separate the primordial CMB signal from foreground contamination caused by our own galaxy and other sources. Planck operated until 2013, producing the most detailed map of the CMB fluctuations we currently possess. The precision of Planck's measurements is almost unbelievable. It refined the age of the universe to 13.8 billion years with an uncertainty of less than 1%. It measured the current expansion rate, the curvature of space, and the properties of dark matter and dark energy with extraordinary accuracy. The Planck map is a work of art and science combined. It shows the CMB temperature fluctuations at a resolution of about 5 arcminutes, revealing structures on scales from the entire sky down to features smaller than the width of the full moon. When you look at this map, you are seeing the universe in exquisite detail as it was 380,000 years after the Big Bang. You are seeing quantum fluctuations from the era of inflation, amplified and frozen into the light. You are seeing the initial conditions that led to every galaxy, every star, every planet that exists today. The map is a snapshot of potential, of a universe poised on the edge of becoming everything it would eventually be. And it is achingly beautiful. Together, COB, WMAP, and Planck have given us a gift beyond measure. They have allowed us to see the baby picture of the universe. They have confirmed the Big Bang theory beyond any reasonable doubt. They have revealed that the cosmos is comprehensible, that its laws are consistent, and that we, with our limited senses and finite lifespans, can nonetheless decode the deepest mysteries of existence. The cosmic microwave background is more than just radiation. It is a message from the dawn of time, and we have learned to read it. What will future generations discover in this ancient light? What subtleties have we not yet perceived? The story is far from over, but we have come so very far from the accidental discovery of a persistent hiss in a radio antenna. The cosmic microwave background has answered many questions, but like all great scientific discoveries, it has also raised new ones. There are mysteries still hidden in that ancient light, patterns that we have detected but not fully understood, and hints of phenomena beyond our current theories. One of the most intriguing puzzles is called the axis of evil, though the name is somewhat tongue-in-cheek. When cosmologists analyze the largest scale fluctuations in the CMB, the features spanning significant portions of the sky, they notice something unexpected. These large-scale patterns seem to be aligned with each other and with the plane of our solar system. This should not happen if the fluctuations are truly random and isotropic as predicted. Is this alignment real? Or is it a statistical fluke, a random occurrence that only seems meaningful because we are pattern-seeking creatures? Scientists are divided. Some argue that with enough data, you would expect to find some apparently anomalous patterns by chance. Others suggest it might indicate something deeper, perhaps a hint that the universe has a preferred direction or axis, which would contradict the cosmological principle that the universe is the same in all directions. There are even speculations that this could be evidence of something beyond our observable universe, perhaps the imprint of parallel universes bumping into ours. These ideas are highly speculative, but they remind us that the universe still holds secrets. Another mystery lies in the smoothness of the CMB. The temperature is almost exactly the same in all directions, to 1 part in 100,000. This uniformity is what we would expect if all regions of the early universe had been in thermal equilibrium, able to exchange energy and reach the same temperature. But here is the problem. At the moment of last scattering, regions on opposite sides of the sky were so far apart that light could not have traveled between them, even in the 380,000 years since the Big Bang. Then did they know to have the same temperature? This is the horizon problem, and it is one of the key pieces of evidence for cosmic inflation. Cosmic inflation solves this problem elegantly. If the universe underwent a period of exponential expansion in its first fraction of a second, then regions now on opposite sides of the observable universe were once close together, able to exchange information and reach equilibrium. Inflation then stretched space so rapidly that these regions were pushed beyond each other's horizons, but they retained the memory of their common temperature. It is a beautiful solution, and the CMB data strongly supports it. Yet inflation itself remains somewhat mysterious. Or what caused it? What was the field called the inflaton field that drove this expansion? When did inflation begin and when did it end? These questions touch on physics at energies far beyond what we can test in laboratories. The CMB also carries potential information about gravitational waves from the earliest moments of the universe. During inflation, quantum fluctuations in the fabric of space-time itself should have been produced, not just fluctuations in matter density. These gravitational wave fluctuations would have left a specific imprint on the CMB, a pattern in the polarization of the light. Several experiments have attempted to detect this signal, called primordial B-mode polarization. In 2014, there was excitement when the BICEP2 experiment announced a detection, but further analysis revealed that the signal was mostly from dust in our own galaxy. The search continues, and if this signature is ever definitively found, it will provide direct evidence for inflation and open a window into the universe at energies approaching the Planck scale. There are other anomalies as well. A slight asymmetry in the power of fluctuations between the northern and southern hemispheres of the CMB sky. Mysterious cold spot, a region slightly larger and colder than what random chance should produce. Are these real deviations from the standard model of cosmology? Or are they statistical artifacts, tricks of small sample sizes and observational uncertainties? Time and more data will tell. Each of these anomalies is a thread that, when pulled, might unravel new physics or might simply reaffirm what we already know. The process of science is not about certainty, but about constantly questioning, testing, and refining our understanding. The CMB is our teacher, and we are still students. Perhaps the most profound mystery is what the CMB cannot tell us. It shows us the universe at recombination, 380,000 years after the Big Bang. But what happened before that? What occurred in the first microsecond, the first nanosecond, the first Planck time? The physics of those moments involves energies and conditions so extreme that our current theories break down. Quantum mechanics and general relativity, our two great pillars of physics, become incompatible at these scales. We need a theory of quantum gravity, a unified description of all forces and particles to understand the very beginning. The CMB can guide us, providing clues and constraints, but the ultimate answers lie beyond its reach, in realms of theory and perhaps someday in new kinds of observations we have not yet imagined. Let us step back for a moment and contemplate what the cosmic microwave background truly represents. It is not just radiation. It is the observable boundary of our universe, a cosmic horizon beyond which we cannot see. When we look at the CMB, we are seeing as far as it is possible to see with light. Before recombination, the universe was opaque. No information from earlier times can reach us via photons. The CMB is the edge of the observable universe in time, just as the cosmic horizon is the edge in space. We are, in a very real sense, living inside a sphere of visibility, and the CMB is the inside surface of that sphere, painted with the light from the earliest moments when the universe became transparent. This raises a profound question. What lies beyond the CMB? not beyond in space, but beyond in time. What happened before recombination? We know from theory and from the evidence encoded in the CMB itself that there was a hot, dense plasma. Before that, the universe was even hotter and denser, back to the first moments of the Big Bang. But can we ever observe those earlier epochs directly? Perhaps. If we could detect gravitational waves or neutrinos from the early universe, we might peer through the CMB barrier. Neutrinos decoupled from matter even earlier than photons, creating a cosmic neutrino background that we have not yet detected but predict exists. Gravitational waves can travel unimpeded through any density of matter. These might be our windows into the very first moments. The CMB also teaches us about the nature of space itself. The precise pattern of fluctuations tells us that space is flat, at least to within the limits of measurement. What does it mean for space to be flat? It means that on the largest scales, the geometry of the universe follows the rules of Euclidean geometry. Parallel lines never meet. The angles of a triangle sum to 180 degrees. This might sound trivial, but it is not. General relativity allows for space to be curved, either positively like the surface of a sphere or negatively like a saddle. The fact that our universe is flat, or very close to it, has profound implications for its total energy content and its ultimate fate. Why is the universe flat? Inflation provides an answer. If space underwent exponential expansion, any initial curvature would have been stretched to near invisibility, leaving the observable universe appearing flat, just as the surface of a balloon appears flat to an ant, because the balloon has been inflated to such an enormous size. This prediction of inflation, that the universe should be flat, was confirmed by CMB observations. It is one of the great successes of the theory, but it also means that the universe we can see might be just a tiny, flat patch of a much larger, possibly curved, possibly infinite whole. We are like sailors on a calm ocean, able to see only a few miles in any direction, unaware of what lies over the horizon. The CMB has also revealed the composition of the universe with stunning clarity. About 5% ordinary matter, the stuff of stars and planets and us. About 27% dark matter, invisible material that interacts only through gravity. And about 68% dark energy, a mysterious component causing the expansion of the universe to accelerate. These proportions are measured from the CMB fluctuations with high precision. But here is the humbling part. We do not know what dark matter is. We do not know what dark energy is. 95% of the universe is composed of things we cannot see directly and do not fundamentally understand. The CMB tells us these things exist and how much of them there is, but their true nature remains one of the greatest unsolved problems in physics. Think about what this means for our understanding of reality. Everything we have ever seen, touched, or measured, every star, every galaxy, every planet, is made of just 5% of what exists. The rest is invisible to our telescopes, detectable only through its gravitational effects or its influence on the expansion of space. We live in a universe where the majority is hidden from us. This should inspire humility and wonder in equal measure. How much do we really know? How much is there left to discover? The CMB has given us answers, but it has also shown us the vastness of our ignorance. And that, in its own way, is a gift. Finally, the CMB tells us about the ultimate fate of the universe. By measuring the expansion rate and the density of different components, cosmologists can extrapolate forward in time. The current evidence suggests that the universe will continue to expand forever, accelerating due to dark energy. Stars will eventually burn out. Galaxies will drift apart until they are beyond each other's horizons. In the unimaginably distant future, trillions upon trillions of years from now, the universe will become dark and cold, with isolated remnants of dead stars and black holes fading slowly into nothing. This ending is called heat death, a state of maximum entropy where no useful energy remains. It is a melancholy vision, but it is also so far in the future as to be almost irrelevant to any conceivable concern. But predictions are not destiny. Physics does not end with what we know today. Perhaps there are phenomena we have not discovered that will alter the universe's trajectory. Perhaps civilizations far in the future will find ways to survive or even escape. Perhaps the universe will surprise us, as it has so many times before. What we can say with confidence is that the CMB has given us a cosmic story, a narrative of beginnings, a description of how the universe evolved from near-perfect uniformity to magnificent complexity, and a glimpse of possible endings. To know this story, to understand our place in it, is one of the great achievements of human intellect. And it all began with the observation of the oldest light. We have traveled together through cosmic history, from the Big Bang to the present, guided by the ancient light of the cosmic microwave background. Now, as our journey nears its end, I invite you to simply rest in the presence of this knowledge. There is a deep silence in the contemplation of the cosmos, not the silence of absence, but the silence of vastness. When you gaze at a representation of the CMB, you are looking at a portrait of the universe as an infant. You are seeing potential incarnate, and there is something profoundly peaceful in that vision. The universe is not chaotic. It is not random, despite the presence of quantum uncertainty. It follows laws, deep patterns that we can discern and understand. The CMB is proof of this. It shows us that the cosmos operates according to principles we can discover. Gravity shapes structure. Light carries information. Time unfolds according to causality. When you understand these patterns, even at a basic level, you gain a sense of order. And in that order, there is comfort. The universe is not incomprehensible. It is knowable. It welcomes our investigation. It responds to our questions with answers written in the language of mathematics and observation. Consider the light that forms the CMB. Each photon has been traveling for nearly 14 billion years, crossing an expanding universe to reach your eyes, or rather, the instruments we have built to see it. In all that time, the photon has interacted with almost nothing. It has flown through empty space, a messenger from the distant past, carrying its information intact. When you detect a CMB photon, you are the first thing it has touched since the moment of last scattering. You are the end of a journey that began before the Earth existed, before the sun formed, before our galaxy took shape. What a privilege it is to be here now, able to receive these ancient travelers and decode their stories. There is a meditative quality to thinking about the CMB. It exists everywhere, uniform and unchanging on the largest scales. No matter where you go in the universe, no matter how fast you travel or in what direction, the CMB is there. It is a cosmic constant, a touchstone of reality. In a universe that is constantly changing, constantly evolving, the CMB remains a testament to what was. It is permanence within impermanence, and there is something deeply reassuring about that. In your life, things change. People come and go, circumstances shift, but the echo of creation persists, unchanged, a reminder that you are part of something enduring. Let yourself feel small for a moment, not insignificant, but small. You are a pattern of atoms arranged in a particular configuration for a brief span of time. You occupy a tiny fraction of space for a tiny fraction of the universe's age. Your concerns, your worries, your triumphs and failures, all of them are local and temporary. Does this diminish their importance? I do not think so. Instead, it places them in context. You are a part of the cosmos, not separate from it. Your atoms were forged in stars. Your existence depends on the laws of physics operating exactly as they do. You are a way for the universe to experience itself, to know itself, to reflect upon its own nature. That is not insignificance. That is participation in something vast. The CMB teaches us about impermanence as well. The universe was once a uniform, glowing plasma. Then it became transparent, filled with neutral atoms and the first light streaming freely. Then stars formed, and galaxies and planets, and eventually life and consciousness. Each stage gave rise to the next. Nothing lasted forever. Nothing was meant to. The universe evolves, and change is its fundamental nature. We too are changing, moment by moment, day by day. Understanding this, embracing this, can bring a sense of peace. Resistance to change is suffering. Acceptance of it is freedom. The CMB whispers this truth across 13 billion years. Everything that exists arose from something else and will give rise to something new. So how should we live, knowing what we now know? There is no single answer, of course. But perhaps we can take inspiration from the cosmos itself. The universe is patient. It operates on timescales that dwarf human lifetimes, yet it accomplishes grand transformations. The universe is generous. It creates beauty and complexity from simple ingredients and simple laws. The universe is indifferent, in one sense. It does not care about your plans or hopes. But in another sense, it is the very ground of your being, the condition of your existence, the source of everything you love and cherish. To live in awareness of the cosmos is to live with both humility and wonder. It is to recognize your smallness and your significance simultaneously. As we approach the end of our journey through the cosmic microwave background, let us return to a simple but profound truth. You are made of stardust. Wes. This is not metaphor. This is literal fact. Every atom in your body except for hydrogen was created in the interior of a star or in the violent explosion of a supernova. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of these elements were synthesized in stellar furnaces and then scattered across space when those stars died. You are made of the ashes of ancient suns. The atoms that compose you are billions of years old, recycled through multiple generations of stars before becoming you. But the story goes deeper. Those stars, the ones that forged the elements of your body, formed in galaxies that grew from density fluctuations in the early universe. And those density fluctuations are visible in the cosmic microwave background. There is a direct causal chain connecting the tiny temperature variations we see in the CMB to your existence right now. If the fluctuations had been even slightly different, the galaxies would have formed in different places, the stars would have had different compositions, and the conditions for life might never have arisen. In a very real sense, the pattern of the CMB predicted you. You were encoded in the universe's initial conditions, a potential waiting to be actualized. This should fill you with a sense of kinship with the cosmos. You are not an accident. You are not a mistake or an aberration. You are a natural consequence of cosmic evolution, as natural as a star or a galaxy. The same laws that govern the motion of planets govern the chemistry of your cells. The same forces that bind atomic nuclei together bind the molecules that make you function. You are not separate from nature. You are nature. You are nature. You are the universe becoming conscious of itself, and that is extraordinary. Of all the things the cosmos has produced, self-awareness might be the most remarkable. And you possess it. What does it mean to be a conscious part of the cosmos? It means you have the ability to wonder, to question, to seek understanding. It means you can look at the night sky and feel awe. You can contemplate the age and size of the universe and experience both terror and delight. You can discover the laws of nature and use them to build, to create, to explore. Consciousness is the universe's way of knowing itself, and every time you learn something about the cosmos, every time you feel wonder at its beauty, you are fulfilling that cosmic purpose. You are the universe, thinking about the universe. How miraculous is that? Species is young. We have existed for perhaps 300,000 years, a blink of an eye in cosmic time. And yet, in that brief span, we have gone from wondering what the lights in the sky are to mapping the cosmic microwave background with precision. We have decoded the story of creation. We have measured the age and composition of the universe. We have looked back across nearly 14 billion years and seen the face of the infant cosmos. This is a testament to the power of curiosity, reason, and collaboration. Science is humanity's greatest tool for understanding reality, and the discoveries we have made about the CMB are among its finest achievements. But knowledge brings responsibility. We now understand how precious and improbable our existence is. We live on a small planet orbiting an ordinary star in an average galaxy, but this planet is the only place in the entire observable universe where we know with certainty that life exists. We are, as far as we can tell, alone. Or if not alone, then certainly rare. This makes Earth and all life on it infinitely valuable. The carbon and oxygen in your body traveled across billions of years and light years to come together as you. Do not waste that gift. Live with intention. Treat yourself and others with the reverence that such a cosmic inheritance deserves. The cosmic microwave background will continue to shine long after we are gone. Billions of years from now, if any beings arise to observe the universe, they will still see the CMB, though it will have cooled even further, redshifted by continued expansion. The story encoded in that ancient light will remain, waiting to be discovered and decoded again. In this sense, the CMB is eternal, or as close to eternal as anything in our finite universe can be. It is a gift from the past to the future, a message that transcends any single civilization or species. It connects all observers across all time who have the curiosity and capability to see it. And so, what have we learned on this journey? We have learned that the universe had a beginning, that it evolved from simplicity to complexity through natural processes. That light carries information across impossible spans of time and space, that we are connected to everything through chains of causality stretching back to the first moments, that the cosmos is comprehensible, beautiful, and vast beyond imagining, and that we, for all our smallness, are a part of it. Not separate, not insignificant, but participants in the grandest story ever told, the story of existence itself. And the cosmic microwave background is the opening chapter, still visible, still speaking to anyone who listens. As our time together draws to a close, I want you to take a moment to breathe deeply and reflect on where we have been. We began by asking if you could hear the echo of creation, and together we have listened to that echo, traced its origins, and understood its message. The cosmic microwave background is more than scientific data. It is a connection to the deepest past, a reminder of cosmic origins, and a testament to the power of human curiosity. When you go about your daily life, remember that the oldest light in the universe is passing through you at this very moment. Invisible, silent, but eternally present. You are immersed in the afterglow of creation, always and forever. There is a concept in philosophy called eternal return, the idea that time might be cyclical, that all events might repeat infinitely. While modern cosmology does not support this literally, there is a metaphorical truth to it. The patterns we see in the CMB, the laws that governed the early universe, these are timeless in their own way. They would operate the same way if the universe began again. The story would unfold similarly, following the same physical principles. In this sense, creation is not a one-time event, but an ongoing process. Every moment, the universe is creating itself anew, following the blueprint written in those primordial fluctuations. You are part of that continuous creation. I hope this journey has brought you peace. In a world that often feels chaotic and uncertain, there is comfort in cosmic perspective. Your problems, while real and important to you, are temporary and local. The universe continues its grand evolution regardless. This is not meant to diminish your experiences, but to contextualize them. When you feel overwhelmed, look up. Remember that you are part of something vast and ancient. The same forces that shaped galaxies are at work in your life, in every life. Gravity pulls things together. Energy flows from hot to cold. Patterns emerge from chaos. These are universal truths, and they apply to you as much as to any star or planet. What questions remain? Kemeni. Science is not about finding final answers, but about asking better questions. We have mapped the CMB, but we still do not understand dark matter or dark energy. We have confirmed the Big Bang, but we do not know what, if anything, came before it. We have detected the seeds of structure, but we wonder if there are other universes beyond our own, forever beyond our reach. Each answer leads to new mysteries, and this is as it should be. A universe fully understood would be a universe with nothing left to discover. And where would be the wonder in that? The cosmos invites endless exploration, and that invitation is a gift. Perhaps one day, future generations will look back on our understanding of the CMB, the way we look back on ancient astronomers who thought the Earth was the center of the universe. Our descendants might know things we cannot even imagine, having developed technologies and theories beyond our current comprehension. They might peer through the CMB barrier using gravitational waves or neutrinos. They might understand dark energy and dark matter as clearly as we understand electromagnetism. They might even discover that the Big Bang was not the ultimate beginning, but a transition from some prior state. And they will build on what we have learned, standing on our shoulders just as we stand on the shoulders of those who came before us. But for now, in this moment, we have what we have: a universe revealed in light. A story told in temperature fluctuations. A past made present through careful observation and brilliant insight. The cosmic microwave background is our connection to the beginning, and studying it is an act of remembrance. We are remembering where we came from, not as individuals or even as a species, but as matter, as atoms, as patterns in the cosmic dance. Every photon of the CMB is a memory of the universe's youth, and by detecting them, we are engaging in the deepest form of anamnesis, the recollection of forgotten truths. As we prepare to part ways, I want to thank you for taking this journey with me, for giving your time and attention to these ideas, for allowing yourself to feel wonder at the cosmos and your place in it. In a universe that is vast and often indifferent, consciousness is precious. Your awareness, your ability to comprehend these concepts is a rare and beautiful thing. You have spent this hour looking backward across time, witnessing the birth of light and the seeds of everything that followed. But you also exist in the present, and you have a future ahead of you. Carry this cosmic perspective with you. Let it inform how you live, how you treat others, and how you face both joy and hardship. The cosmic microwave background will be there tomorrow and the day after, and for billions of years to come. Are you? It is patient. It does not demand your attention. But whenever you wish to return to this feeling, this sense of cosmic connection and wonder, simply remember. Remember that you are made of star stuff. Remember that the oldest light surrounds you. Remember that the universe is both incomprehensibly vast and intimately knowable. Remember that you are a way for the cosmos to know itself. And in remembering, perhaps you will find the peace and perspective that comes from understanding your place in the grand story of existence. The echo of creation is always there, always waiting, always speaking to those who listen. Thank you for listening with me. Our journey through the cosmic microwave background comes to an end, but the echo of creation continues forever. The next time you look at the stars, remember that you are looking back in time, witnessing photons that began their journey long before you existed. And remember that the oldest light of all, the CMB, is passing through you right now, connecting you to the first moments of the universe. If this journey brought you peace or wonder, I invite you to explore more of the cosmos with me here at Cosmic Calm. There are infinite stories written in starlight, and we have only just begun to read them. Until we meet again, may you find peace in the vastness and comfort in the knowledge that you are, and always have been, a part of something magnificent. You are the universe, awake and aware. Rest well, cosmic traveler.